R script, and then let us load our data. Let's call it DF, but instead of just calling DF, let us call it blood pressure. Let's call it blood pressure. Then Alt. Okay, what we do first is loading our packages. So number one, let's load our packages. And we are going to load which package? I don't think we need any of the packages today, but it's okay. Let's load the data. Loading the data, let's call it to this blood pressure. And because it is in form of a text, we are going to use read.delim. That's delim means delimiter, whether it is a comma delimited file or I mean a CSV file or a text. This one is a text. So the delimiter here is a text. So for easier work, we said you just write file.choose. Just put that outside that bracket, then write header. Let it be true, capital T. And the separator, what is separating? It's a comma delimited file, so the separate is a text. So it is a text. Put that that I think it is a forward slash or a backward. I don't know. It's is it a backslash or forward? That slash, then text, that for a T for a text. And then let us run that. Let's see what happens. It gives me this. Then I go to where that data set is, blood pressure.text. Okay, there is a problem. SEP is equals to, okay, not this slash, but the other one. Let's see. Taking some time. I don't know what's up. Run that. Okay, it came over here. So this is where I have my data, blood pressure text. Okay. So that one. So let me run it once more. It is not popping up as I wanted it to. So blood pressure. Okay. Yeah, so let me view my blood pressure. Yeah, here's the data. So this data set is of some people who are given some medicine. Let's say you have a problem with your blood pressure. So there is some medicine, maybe a vaccine that has been developed. So your blood pressure is taken before you're given this medicine or this vaccine, and then then after you have taken the medicine or the vaccine, your blood pressure is taken. So you'd like to know whether there is a difference, whether this drug is really working. So you'd like to know what is the mean blood pressure before and the mean blood pressure after the vaccine has been administered into your body. So these are different subjects. As you can see, this is before and after. So this is the same individual. So this person is the same. The first person was, these two tests were done on that same person. So this is a paired data set. So these are where you do a paired t-test. That's what we call, that's why we call it a paired t-test. These are not independent samples, but they are not independent samples, but paired. So when you have such a data, let's first plot it. Let's do a box plot. Just write a box plot of your. So for easier work, let's attach that data. Let's attach our blood pressure. Let's attach it, and let's have a box plot of before and after. let's see whether this works just as it is blood. So whether that can be. So this should not be here. So let's specify what we want. We want to have a plot of before and after, whether there is a difference. So from this box plot, as you can see, this was before. So the blood pressure is very high. After the medication or the vaccination, the blood pressure dropped, as you can see here. At least you can see from this box plot that there is a difference of the mean blood pressure before and after. Another plot we can make, let's just make a scatter plot of before and after again. The after, see what happens. So this is just a scatter plot. So let's make a 90-degree line called AB line to see whether there will be a difference. AB line is just a AB line. Let's a 90-degree line, like A is equals to 0 and B, which is a gradient, is equals to 1. Let's see what happens. Yeah. So look at this line. So this was before the vaccine, this after the vaccine. So is there a difference? As you can see, the points here are more than they are here. So you can say that there is a difference in blood pressure. Blood pressure seems to have decreased. So if the vaccine did not work, this should have been the same. The distribution should have been the same. But since it shows that after the vaccination something happened, the blood pressure reduced, then you can have an idea of what is happening. Let's put after, then before. After, before. Then do the line again. Just interchange the scale. So before there are more points before than after. So they show that there was a change in the blood pressure. So let's do our paired t-test. So our paired t-test, let's put paired t-test. Now let's have our HO, our null hypothesis. So we'll say that the mean blood pressure, before is equal to mean blood pressure after the vaccination. So the differences, they are not, the differences are equal to 0. So when you take the blood pressure, the mean blood pressure for before and for after is the same. So the alternative hypothesis will be that the mean blood pressure for before is not equal to the mean blood pressure for after the vaccination. So let's do a t-test. It is simple. Just say a t.test. T.test. And last time we said if you are stuck somewhere and you like some assistance or help with what you want to do, just write a question mark. You type a question mark before the function t.test. And when you run that, it gives you, should give you a student t-test, what you're supposed to do. It gives you a description if you get lost in some way. Okay, so okay. Let's go on. Now, we want a t-test of after. So what after and before? You can run that. You can see. So there are some additional functions you can add just for your own use, but these are usually the default. So for example, you want to say the mean, the difference in means is equals to 0. There's no difference between the means. You can put the confidence level, which is equal to the confidence level. You want it to be maybe 0.95 or 0.99, whatever you like. And then, most important, you have to say that these are paired. So true. These data sets are paired. They are not independent. Then you run that. So let's come to this. Let's try now to understand this output. So the data is after and before. This is the test statistic of negative 3.882. The degrees of freedom are 24. That means there were 25 minus 1. So the p-value is 0.006. So this p-value is less than 0.05. So whenever the p-value is less than 0.05, what you do to the null hypothesis is that you reject it. And you say for sure that there is a change for after and before. And the differences in the means is -8. So there's a 0.8 reduction in the mean blood pressure when they administered the vaccine. And that's how you do a paired t-test. Secondly, let's assume that this data was not normally distributed. So this paired t-test is a parametric test. Now we would like to do a non-parametric test if assuming that the data was not, depending on the collection of the data and its distribution, we say that the data was not normally distributed. Now we do a non-parametric test. So an equivalent non-parametric test of t-test is what we call the Wilcoxon t-test. And it is the same way. So Wilcox.test is put after, the difference between after and before. You have to say that this is a paired, true, and it's a paired test. So, but now in this, in Wilcoxon the test, what we do, we don't test for the mean, but in this case, we test for the median. So you can say that the median for both the sets of data are equal, meaning there is no significant difference between before and after. So this, so what is the p-value? The p-value is also here less than 0.05. So even if you're using the non-parametric test or the parametric test, you'd have to reject the null hypothesis because at least there is a change, there is a difference of 0.8. So the blood level, the blood pressure drops by 8 points. So that's how you do a paired t-test. Any questions up to that point? Any clarification? Any problems?
I think I missed something on the t-test command where you write t-test, then bracket, line number 12.
Okay, so this
I see something. Yeah, the mu equal to 0.
Yes.
I didn't get it.
This is the mean. You are assuming that the difference between the means is 0. So let's say maybe someone looked at us, you and I, and said that these people are the same age. The differences between their ages is 0. So if you take the age of that person, your age minus my age is equals to 0. So there's no difference in our ages. So that's what it means, that the mean difference in blood pressure between after and before is equal to 0. That is what you are testing against. That there's no difference. There exists no difference between the means of after and before. Is that okay?
Yeah, I got it right now. Thanks.
All right. Now that was a paired t-test. Something else we can do, let's now do two sample t-tests, or what you call the independent tests. For this, we are going to load another data set. I don't think some of you have it, I'm not sure. There's a data set here on chick data. Chick data. It's a CSV. So let's just load it. So let's call it. This is chick data. Chick data. Let's load that. So row 3. Let me just these people.
Very well. Thank you very much.
Okay. Let's download this data. Okay, which is a file dot choose. There's no need of putting header or separator or anything like that, because chick data, it's already a CSV. Okay, let's view it. View chick data. Okay, so here we have two columns of data set of weight. Maybe this is a weight gain, and this is a feed. So we want to know if you feed these chicks, maybe you are a supplier of Ken chick, and you are trying to test two meals whether they work well. So you have two feeds. One is meat meal, and the other is casein. I wonder if casein, I think a lot is a poison, but it's okay. Now we have weight gain. This is the weight that is gained, and this is the feed. So we want to know whether any of them, where either of the two has a better weight gain compared to the others. So so in this case we do, because we have two independent samples. Here we use two independent sample t-test. So let's plot as we did. Let's plot. We are plotting the weight gain, that is the weight gain, I believe, and it's a tilde, and the feed. Let's see whether there exist any differences. From this box plot, the meat meal seems to be, the gain in weight seems to be lower, and the casein seems to have a higher weight gain, but with higher variation. You can see this box is larger, so there's a higher variation there. Okay, so let's try to see what happens. Okay, so the same way, t.test, just the same way. We have take the weight. It's supposed to be weight, and this is feed. The differences in means is 0. We assume that there's no change in any. So let's say, okay, let's attach this data. So that's data. Okay, and this paired is equals to false, because these are not paired, these are independent. Let's see our result. So the p-value here is 0.09. This p-value is greater than 0.05, meaning that the weight gain between the two feeds is the same. There is no significant difference. You might, and the mean for for casein is 322.58, I think, grams, and this one was 276. As you can see, there are differences, but t-test tells us that this difference is not significant. Why is it not significant? Mostly because of the variation that are, you see the variation here is too high. This variation is the one that is causing it to be said that the two, the weight gain between the two feeds is the same. So once again, let's say that this data was not normally distributed. We also do a non-parametric test, which is Wilcox, again, Wilcox.test. So weight and feed mu is equals to 0. Mu is equals to 0. The difference in means is equals to 0. And paired, is it paired? Is equals to false. These ones are not paired. These ones are independent. As you can see, the p-value is still higher. So the median is not significantly different. The median of the two samples of the two means is not significantly different. So you can use either because there's no significant difference. So if you're using meat meal and you wanted to change it to this casein, but you see there's no significant difference, then you might say instead of spending more on this meal, on this casein, let me just continue with my meat meal. So the only difference between the paired t-test is that this one paired is true, you put true, and this one paired is equals to, in here, paired is equals to false. And yes, that is it. That is what I wanted us to do today. Now, there is what we call, let's have a report of this, of our work. So let's call it library R Markdown. This is R Markdown. Then go to this and unique, just click it and then unit it. Oh, first, let's save this script and let's call it. Sorry, let's come over here and save. Let's save it as t-test, just t-test. Okay, then let us generate that what we've just done. This is R Markdown. It generates the work we've done. The reason it was not working, it was not working because I had written here plot instead of a box plot. As you can see here, let's use a plot first. It can't work because this is a plot. A plot is like I'm trying to create a scatter plot, and the data is not numerical data. Is not numerical data in both categories because you have one numeric category and you have one numerical whatever column and another categorical column. So we can't use plot. Plot makes scatter plot. So the mistake I did is failing. I would have said a box plot. We want a box plot instead of just a plot so that it works. So having done that, now you can go over there and let's compile that. Let's hope this time it works. Yeah, it works. Let's see what it gives us. So this is a report. This is what we have done. This is what we did in the first place. We drew the box plots for the first one. We continued all the way. We made this scatter plot, we made this line. So this gives you a report of everything that you did, and that is good for reporting. And you can also make it into what you call, you can convert it to a PDF or an MS Word. Let's do for an MS Word, see what happens. Give it some time.
Yes, I can see it.
This is a good thing about R and the reporting. It does this. You need this document has every code that you create, that you coded, you created, and the plots that you made are there, and everything that you did in your R environment, in your R source, it's reported here very well. Whatever you write, it is recorded and can be able to report this. So that is it for today. And so I hope now you are conversant.
Hello, Dan.
Yes.
Please, non-parametric data, we use Crucial or that one you have shown us. Wilcox.
Okay. Last time we talked about ANOVA. ANOVA is when you're comparing three or more means of data, right?
Yes.
So when you're talking about ANOVA, the non-parametric tests, when the data is not normally distributed, instead of doing ANOVA, that's when you do a Kruskal-Wallis test. But for t-test, you do a Wilcoxon test. You understand the difference? So
yes,
the Kruskal-Wallis test, you do it when you're doing ANOVA. If your data is not normally distributed, is an equivalent of ANOVA, a non-parametric test for ANOVA. And this Wilcoxon test is an equivalent of a t-test, whether paired or independent t-test. Okay? When you're talking about t, so t-test is an unparametric for t-test is the Wilcoxon test, and for the other one, the ANOVA, is when you use the Kruskal-Wallis test. I hope you get the difference.
Dan.
Yes.
What about the Tukey's HSD?
The
Tukey's HSD test.
You do Tukey when you're comparing means when you don't know what is different from what. But in here in a t-test, you know that they are different, and which is different for there are only two. There is no comparing more than three, so you don't need a Tukey HSD test. Is that okay? For example, let's come to one of our t-tests here. Let's try this. So you are comparing only two means. Oh, this one was a pair, so the difference in means was a -8. Let's go to the unpaired one. Let's try that. You know the mean of Kasen, this is the mean, and the other mean of this one. So, and it's only the two which are different. Okay, so you don't need to do a Tukey. Tukey is done for ANOVA, the one with more than two means, so that you can know which means are different from the other. So for t-test, you don't need the Tukey HSD test. Okay.
Yes. So it means that in our previous assignment, we should have gone up to Kruskal-Wallis.
Yeah, the previous test was about ANOVA, so you should have gone. You must have gone up to the Tukey HSD, the other assignment. Remember?
We did the Tukey's HSD.
Yeah, because you are comparing more than two means, so you wanted to know which means were different from the other. But this one, you have only two. We know what we are talking about, so there's nothing we don't know in this case. We are talking about only two means, and they're either different from one another or they are equal. As you have seen this one, that these ones, the means here are equal. Any more questions?
Yes, Dan.
Yes.
About saving your data into either MS Word, PDF, or HTML. I want to know. I saw you going somewhere. I saw you going somewhere.
All right.
Because of the network.
Okay, so what you do, you just go up here, file. See file? File here. Click that, then just save. Mine is already saved. Let me create another script so that I can save it. So let's create a new R script. There it is. You write your code here and all that. Then I want to save this one, so save it. File, then save. Then it comes to your R environment. Just write the name of that R script. Maybe we want to call it your name, Melvin. And so it is saved that. So when you want to knit and create an R markdown, you just click this notebook to compile. Is that okay now?
Yes.
chi-square test, and then yes.
I'm just trying like to save my script, the one we've been doing now, and it's telling me the file was created as an R script. However, the file extension you specified will change it to another file type.
Okay.
So it's asking me if I'm sure I can change the file to another file type.
Another file. Yeah.
When I come to file,
save,
and then I say t-test. And then when I say save, it tells me that.
Okay. Don't write dot. Remove dot. Don't write dot test. When every time after test, give the extension of that file, the format of the file. So don't write dot text at last. Just write. Don't put a dot anywhere.
So
yeah. Because now it should be dot R because dot R.
And can you put a hyphen?
No. Just,
can you put a hyphen?
Yes, a hyphen you can. Hyphen you can. Yes, hyphen you can. Sorry, you can put a hyphen. Okay. Save it now.
Okay, yeah. I see. That is what I was like getting confused about.
All right. I hope you're okay. That I can see now it's okay now. So don't put, well, you see it is written t-test.r. It's an R script. So you are putting another extension of something that it didn't understand. Okay, the format it didn't understand. Okay, so